D to A works as follows. Also, this is not completely correct because you would have low-pass filters that would shape the bandwidth. So there's other things going on, but this will end up being a fairly good approximation of reality. Assume D to A works as follows. So if I have a sample at time k in discrete time, then that sample, D to A replaces that sample with a rectangle. So this is, actually, I'm going to use, sorry, if I have a sample at time j, because k is my index, k is my time index. If I have a sample at time j with amplitude S0 of j, then I replace that with a rectangle that lasts from j minus 1 ts, j ts in time, and has constant amplitude S0j. So this is one of the possibilities for a digital to analog converter. It wouldn't be exact, but this is idealized. And other models probably won't return a significantly different answer for the energy. So this is, what this is going for is that it's nice and simple. So for instance, polar NRZ, let's say polar NRZ with ND equals 4. This is S0 of k. So to get, or these are all equal to 1, to get S0 of t, we just fill it in with rectangles behind each sample with the same amplitude. So there's 1, 2, 3, 4 equals NB. So we have one rectangle that lasts from, so 1 minus 1 is 0 times ts, that's 0, to 1 times ts. Another rectangle goes from ts to 2 ts. Another rectangle goes from ts to 3 ts. Another one goes from 3 ts to 4 ts. And furthermore, 4 ts happens to be TV. So in fact, S0 of t looks like this. And if we take another example, BPSK. With NB equals 8. BPSK with NB equals 8, it basically looks like a sampled sine wave. So at 4 and 8, which is NB, it's equal to 0. That's S0, okay. So S0 of t look like this. There's S1, so that's a box that goes like that. There's S2, a box that looks like that. S3, S4. The sample at 4 is 0, so there my rectangle actually sits on the axis. S5, S6, S7, and S8, again I sit on the axis like that. That is 8 times TS, which is equal to TB. So in fact, S0 would look kind of like this. Which is sort of a squared off version of a sine wave. All right, so now we can calculate energy per bit. In fact, we can come up with a general expression for energy per bit. So let's let R, so to do that, let's come up with an expression for whatever the rectangle is. Let's call it R sub Ts of T. And that will be equal to 1 from time minus Ts is 0 and 0 elsewhere. So in other words, it looks like this. So why do I define it sort of on to the left of the y-axis? Is because whenever I have a sample, the square goes to the left. In other words, I'm just going to be shifting this over by Ts times the number of samples. That's where it's going to go. So the output of my my continuous time signal corresponding to my analog signal will be, let's say, S. So going from S0K to S0T, S0T will be equal to the sum from I equals 1 to NB. So over all the samples in S0, which is only defined, should only be defined from 1 to NB, of S0I, so the value of the sample multiplied by the rectangle that's shifted into place to take that sample position. And that will be R of T shifted. So we shifted by subtracting the amount of time we need for the shift. And the amount of time we need for the shift is I times Ts. So does that work? If I want, remember what I wanted sample I to turn into a rectangle from I minus 1 Ts to I Ts. So the multiplication does the job of making that equal to S0I. And this shift will take the rectangle from 0 and shift it over by exactly ITS. That's exactly how that works. So what's the energy? E0 is equal to the integral from 0 to TB of S0 T squared dt, and S0 T squared is given by this. So this is the integral from 0 to TB of the sum from I equals 1 to NB, S0I